With this video, we begin a series of explanations for how the reaction rate is related to the mechanism of the reaction. In prior videos, we have explained introductory concepts in chemical kinetics, the first of which was the definition of the rate. Then we also looked at how the rate depends on the concentrations, and that is the rate law. And we also looked at how the rate of a chemical reaction depends on the temperature through the Arrhenius law. All right, one of the main points that we made in those prior videos is the fact that when you have a chemical reaction, the rate law needs to be determined with experiments. You simply cannot write the rate law directly by looking at the reaction stoichiometry. That is exemplified by a typical enzyme-substrate reaction that follows Michaelis-Menten, in which the reaction looks like enzyme plus substrate yields enzyme plus product. Okay, but the rate law, okay, the initial rate, is equal to something that looks rather complicated. Again, this is an example for how, just looking at a particular chemical reaction, we can't go and look at the reaction stoichiometry and then be able to write the rate law. The reason that we actually cannot do that is because in any particular reaction, it's not always obvious whether the particular reaction takes place in a single step directly, or whether there's an underlying mechanism involved. For example, in the Michaelis-Menten mechanism, the reaction does not proceed directly. Instead, there's a sequence of steps that the reaction goes through. The first step is the binding of the enzyme to the substrate to generate an enzyme-substrate complex. And this first step actually happens to be reversible. Okay, that will be step one of the reaction mechanism. The second step, okay, is the one that yields an enzyme product complex from the enzyme substrate complex, okay, and is generally not reversible. And then there's the last step in which the enzyme product complex dissociates into enzyme plus product, okay, and that also happens to be reversible. Well, it turns out that this reaction mechanism is actually embedded into the rate law. Indeed, there is a direct correlation between the rate law and the reaction mechanism. Okay, so what we're going to be doing in the next few videos is try to delineate this connection between the rate law and the reaction mechanism. Okay, so that by examining a reaction mechanism, then we will be able to actually write the rate law, derive the rate law, or even better, if we have a new chemical reaction, we can always determine the rate law using, for example, the differential or Van Hoff method or the integration method. And if we know this rate law, then we might be able to actually figure out what the reaction mechanism is. Okay? So in this video, we actually, besides this introduction to the connection between the reaction mechanism and the rate law, we're going to introduce a very important concept, which is the concept of the elementary step. Okay? So this is what we call the orbital reaction. And the orbital reaction has a mechanism. This is the mechanism. Okay, so the mechanism consists of elementary steps, which are reactions that occur directly. For example, this first step right here in this mechanism is what we call an elementary step, because you can see from the reaction the process that is taking place. Right? So what we understand here is that the enzyme is approaching the substrate, or the substrate is approaching the enzyme, and they bind and they generate a complex. Okay, that only requires one step, which is again the binding of the two substances, and that is what constitutes an elementary step. Okay, another example of an elementary step. Let's take a look at the reaction oxygen plus H2 hydrogen to generate OH plus H. You can see that this reaction actually occurs in just one step, and therefore is an elementary reaction, in that in order for the reaction to take place, the only thing that needs to happen is that this bond breaks and then a bond is formed. So you can envision how the mechanism of this reaction is. Oxygen simply approaches H2, and then when the OH bond is formed, then the HH bond is broken, and then you generate OH plus H. Okay, so that will be just an elementary step. So here's something very important. When you have an elementary step, then you can write the rate law for that elementary step just by looking at the reaction stoichiometry. Okay, so for example, if we were to write the rate law for just this step, not the reversible one, but enzyme plus substrate to BBS, the way that we would actually do this is by doing the following. Rate is simply the rate constant multiplied by the concentration of enzyme to the power of the stoichiometric coefficient, which is just 1, and then times the concentration of substrate to the power of the stoichiometric coefficient, which is just 1. This is the rate law for this particular elementary step. Okay, so again, it's quite important. Once you have the elementary steps, or if you're convinced that a chemical reaction occurs in just one step, then there is a direct correlation between the rate law and the reaction stoichiometry. Okay, so for this reaction, the rate law would be like this. Okay, concentration of oxygen times concentration of H2. Okay. Now, we can classify elementary reactions or elementary steps according to something that is called the molecularity of the elementary step. And the molecularity simply is the number of species involved, the number of reagents involved in that particular reaction step. Okay, so if there's only one reagent, then the elementary step is called unimolecular, and the reaction will be first order. Okay, so for example, let's assume here a reaction in which simply you just have A turning into B. And this is just an elementary step, for example, a cis-trans isomerization, as it happens in retinol through the process of vision. Okay, so then the rate is simply equal to K concentration of A to the power of 1. That's a unimolecular elementary step, and the reaction happens to be first order for that step. Okay, most reactions that we actually know are bimolecular, or most elementary steps are bimolecular, and then the rate law would be second order. The reaction would be second order overall, first with respect to each one of the species. Very rarely we're going to have elementary steps with molecularity higher than 1 or 2. There are occasional reactions in which you have 3 reagents. Okay, this would be one of these species, or one of those reactions, in which you have 2 iodine atoms colliding with different species to generate I2 plus the same species. This would be a termolecular reaction, and the rate law would be just rate is equal to the rate constant times the concentration of I squared times the concentration of M would be a third order reaction overall. Termolecular reactions are very rare in the gas phase. This will be a reaction that takes place in the gas phase, because in the gas phase it's extremely, statistically very, very difficult to actually be able to obtain 3 species in the same region of space. Okay, in solution, thermomolecular reactions are a little bit more frequent, but we're not going to be talking about many of them in these videos. Okay, so just to wrap things up, we have established the first connection between the reaction mechanism and the rate law of a reaction. We have said that when you have an elementary step in a reaction mechanism, that elementary step, the rate law for that elementary step can actually be the rate law for that elementary step can be written directly from the reaction stoichiometry. Okay, so in the next videos we're actually going to be analyzing complex reaction mechanisms and see how the rate for the overall reaction can be written from the rate laws of each of the individual steps of the reaction.